and the meeting will be posted on YouTube, just so you know.
Wait, coming right.
All right, so today's lecture is on aldehydes and carboxylic acid derivatives. My name is David. I'll be presenting the lecture today. So like I said before, this video is being recorded. So if you need to change your profile picture or your name on your Zoom, you can do that. So we are recording this lecture and then posting it on YouTube too. So this is just a consent for audio video recording. I posted the link at the bottom of this page to the full consent form if you want to check it out. So just a quick description on the course. So we are doing a 15-week MCAT course. We are doing Zoom lectures every Thursday, Friday, and Saturday at 8:30 p.m. EST. And then on Sundays at 8:30 also, we're doing office hours. So if you have any questions or problems you want to go over, you can check it out on Sunday. And just some useful links for you. We do have a group meet chat if you aren't in it already. You can post questions on there or ask for general advice. Like I said before, we do have a YouTube channel where we post the live recording, and then we also cut up the recording into 10-minute mini videos if you want to check that out. And we do have a website, socraticmed.net, if you want to check that out as well. And then if you want to follow the Instagram page, you can for daily updates. Just some useful links for you. So some learning objectives for today. I'm going to go over aldehydes and ketones and some reactions involving them. Next, I'm going to also go over enolates and aldol condensation. And finally, I'm going to review the carboxylic acid derivatives and some reactions involving them as well. So first, I'm going to go into aldehydes and ketones. So as you may know, aldehydes, they only have one alkyl group and one hydrogen bond attached to the carbonyl. They are always a terminal group, so they're always at the end of the molecule. And when naming them, they have the suffix Al at the end when it's the highest priority functional group in the molecule. So on the bottom right, I just have the general structure of an aldehyde. So as you can see, it has a central carbon that has a carbonyl, so it's double bonded to an oxygen, and then attached to an R group, which is usually an alkyl chain, and then finally a hydrogen as well. And then on the picture below, you can see there's just 5 general aldehydes that you'll commonly see on the MCAT. Some of them have more specific names. So methanol they also refer to it as formaldehyde, ethanol as acetaldehyde, propanol as propionaldehyde, butanol as butyraldehyde, and pentanol as valdealdehyde. So usually the first 4 are the ones that they mostly use, but just be aware that they can have 2 different names to them. And it's helpful to know what the group looks like. So in how they're connected and what the alkyl group is. So that's aldehydes. And then ketones, they're similar to aldehydes, except they have 2 alkyl groups bonded to them instead of just one, like in aldehydes. So since they have 2 alkyl groups bonded to them, they're never a terminal group. You'll always find them at the center of a molecule. And when it's the highest priority functional group, you'll see the suffix "-one" at the end in the IUPAC name. So ketones, look similar, but instead of hydrogen also bonded to the carbonyl and the other alkyl group, it's usually another alkyl group bonded to it. And so for aldehydes and ketones, you'll usually see the prefix oxo when it's not the highest priority functional group. So when there's like carboxylic acid also on the group, when it's not the highest priority functional group, you'll see it referred to as oxo in the IUPAC name. And then they also use the prefix keto for ketones. So for when they're named as substituents, you'll see aldehydes and ketones referred to as oxo. And then also for ketones, they use keto as well. So that's just aldehydes and ketones. So you can form an aldehyde by partial oxidation of a primary alcohol by PCC. So PCC is a mild oxidizing agent, so it won't oxidize the primary alcohol into carboxylic acids. It'll stop halfway. It'll oxidize it to an aldehyde instead. And for ketones, any secondary alcohol, any oxidizing agent will oxidize the secondary alcohol into a ketone. So PCC will oxidize the secondary alcohol into a ketone, but then anything stronger like Na2Cr2O7 or potassium dichromate or the Jones oxidation will turn the secondary alcohol into a ketone. So those are some reactions on how to form the aldehydes and ketones. So just some physical properties on aldehydes and ketones. Their properties are governed by the presence of the carbonyl. So the carbonyl determines the bonding and other interactions of aldehydes and ketones. So the carbonyl is polar, and the molecule is polar, but there is no hydrogen bonding because there's no hydrogen attached to the oxygen in the carbonyl. So because there's no hydrogen, there's no hydrogen bonding between aldehydes and ketones or aldehydes and ketones with any other molecule. But the carbonyl, it acts as an electrophile due to the electron withdrawing properties of the oxygen attached to the carbonyl. So because the oxygen is more electronegative than the carbon, it'll pull more of the electron density to the oxygen as a result, and this causes a partial negative charge on the oxygen and then a partial positive charge on the carbonyl carbon. And this causes the carbonyl carbon to act as an electrophile and interact with nucleophiles that are able to donate electron density. So at the bottom, you can see here, because of the electronegativity of the oxygen, more of the electron density is drawn towards the oxygen, and that results in a partial positive charge on the carbon and partial negative charge on the oxygen. And when reacting, aldehydes are more reactive than ketones just because there's less steric hindrance and less electron donating alkyls. So because of the extra alkyl group in ketones, there's more steric hindrance, and alkyl groups are weakly electron donating, so that causes it to be less effective as an electrophile. All right, any questions on ketones or aldehydes before I go into a question? All right, you can unmute or just put in the chat if you have any questions. Mark is also here today, so if you have any questions during the lecture, you can put in the chat and he'll help you out. All right, if there's no questions, give everyone this problem. So on the right, how many ketone groups are in the following molecule based on the picture on the right? All right, I'll give everyone a few minutes for this. Let me start the poll. All right, take a few minutes to answer this question. Opal. So today's topic is aldehydes, ketones, and carboxylic acid derivatives. Take a few minutes for this question. All right, I'll give everyone a few more seconds if you want to try and answer this question. All answers are anonymous, so put in your best guess if you're not sure. All right, I'm going to end the poll now. And there were some mixed responses, but the answer is A. So in this molecule, there's a few amide groups, a few esters. They're all trying to confuse you. So there's only one true ketone group, and it's this one right here. So ketones, it consists of a carbonyl and then two alkyl groups attached to it. So this is the only group that has two carbons attached to it. All the other ones, like this one, is technically an ester. This one's an amide. Yeah, so this group right here is this is the only true ketone group in this molecule. Any questions on this this problem?
You said a ketone group consists of a carbonyl and what else attached?
And two alkyl groups attached to it. So it has to be attached to two other carbons.
Thank you.
No problem. Any other questions about this problem? All right, I'll move on to the next topic. So next, I'm going to go into some reactions involving aldehydes and ketones. So first, I'm going to go over nucleophilic addition to carbonyls. So like I said before, the carbonyl is polarized because there's a partial positive charge on the carbon and a partial negative charge on the oxygen due to the difference in electronegativity. So nucleophilic addition is when a covalent bond is formed on the carbonyl carbon when a nucleophile attacks and breaks the double bond that it has with the oxygen. So what happens is the oxygen accepts electrons donated by the nucleophile, and then this causes the formation of a tetrahedral intermediate. But the carbon won't reform because there are no good leaving groups attached to the carbonyl carbon. So what happens is the oxygen will accept a proton from the solvent, and this forms a hydroxyl group. So this is the mechanism for the reaction. So as you can see here, this blue nucleophile, it'll attack the carbonyl carbon due to the partial positive charge. This causes the electrons from the double bond to move on to the oxygen, and this causes a negative charge on the oxygen. And since aldehydes and ketones, they don't have any good leaving groups attached to it, it won't be able to reform the carbonyl by kicking off one of the substituents. So what happens in aldehydes and ketones, the anionic oxygen will accept a proton from the solvent, and this forms an hydroxyl group. So this is the final product in a nucleophilic addition to the carbonyl in aldehydes and ketones. Next, so hydration of aldehydes and ketones. This is similar to when I went over protecting groups for alcohols. So what happens is an aldehyde or a ketone will react with water to form geminal diols. So this is when there's two oxygen groups attached to the same carbon. So what happens is the nucleophilic oxygen in water will attack the electrophilic carbonyl carbon, and this will form a tetrahedral product as well. So as you can see on the bottom, the carbonyl oxygen will accept a proton from the solvent, and then the water attacks the carbonyl carbon, and that resonates the electron from the double bond onto the oxygen, and this takes away the positive charge. And in order to form a neutral product, the solvent will take back that proton, but from the other oxygen that was just added onto the carbonyl carbon, and this forms a hydrated aldehyde or ketone. So that's the hydration mechanism for aldehydes and ketones. Next, I'm going to go into acetals and ketals. So acetals are formed when aldehydes are reacted to two equivalents of an alcohol or a diol, so a molecule with two hydroxyl groups attached to it. So this forms a primary alcohol with two alcohol OR groups attached, and also a hydrogen as well to the central carbonyl the carbon that was in the carbonyl. When only one equivalent of an alcohol is added, it forms a hemiacetal. So aldehydes, when reacted with one equivalent of an alcohol, it forms a hemiacetal. So only one oxygen is bonded. But when it's reacted with two equivalents of an alcohol or a diol, it will form an acetal. And similarly, ketals, this is when a ketone is reacted with two equivalents of an alcohol or a diol. This forms a secondary alcohol with two OR groups attached to it, so alcohol groups attached. And when only one equivalent of an alcohol is added, a hemiketal is formed. So hemiacetal and hemiketal, this is when only one equivalent of an alcohol is added. So like I said before, this is used for protecting groups for carbonyls. So this could prevent the aldehydes from being oxidized or reduced, and prevents the ketals from being reduced. And you can revert back to a carbonyl, so deprotect it by using aqueous acid in order to convert the acetal, hemiacetal, or ketal or hemiketal back into an aldehyde or a ketone. So this is just the mechanism or the reaction. So when one alcohol group is used, a ketone forms a hemiketal, and then when another alcohol group is used, it forms a ketal. Same thing for aldehydes. Aldehyde with one equivalent of an alcohol forms a hemiacetal, and when another is used, an acetal is formed. And it can be one step if a diol is used. So instead of a molecule with only one hydroxyl group added attached to it, a molecule with two hydroxyl groups, so a diol would complete this reaction in one step. Next, oxidation and reduction of aldehydes and ketones. So like I said, you can form an aldehyde from a primary alcohol using PCC, but when you oxidize an aldehyde with any oxidizing agent stronger than PCC, then you can form a carboxylic acid. So anything like potassium dichromate, sodium dichromate, or the Jones reagent, it will form a carboxylic acid when reacted with an aldehyde. But ketones, they're as oxidized as secondary carbons can get. So no matter how strong the oxidizing agent is, you can't oxidize the ketone further. But when you react ketones and aldehydes with a reducing agent like hydride reagents, like lithium aluminum hydride or sodium borium hydride, you could form the alcohols that oxidizing agents would form aldehydes or ketones. So when you use the reducing agents on an aldehyde, it would form a primary alcohol again. And then when you use the hydride reagents on a ketone, it would form a secondary alcohol. So on the bottom, as you can see, this is the reduction of an aldehyde back into primary alcohol. So that's oxidation and reduction. Any questions before I give everyone this problem? Okay, all right. If no one has any questions, I'll give everyone this problem. The reaction between 1 mole of acetone and 1 mole of propanol and aqueous acid will result in the formation of what product? So let me start the poll. All right, so the poll started. Take a few minutes to do this problem. All right, I'm gonna stop the poll in a few seconds if you want to get your final answer in. Okay, I'm gonna stop the poll now. So most people chose choice B, but the actual answer is choice A. So acetone, if you remember, I said ketones, they end in O-N, O-N-E, so one, and then aldehydes, they end in al, so Al. So acetone is a ketone. So when you react ketone with propanol, an alcohol, this results in a hemiketal. So that answer is hemiketal. If it said 1 mole of acetone and 2 moles of propanol, then the answer would be a ketal. But since it's only 1-to-1, so there's only one equivalent of an alcohol, it would only form a ketal. So it would only be 1 alcohol added to the ketone group. Does that make sense? Anyone have any questions on this problem? You can unmute or put in the chat if you have any questions. Okay, all right.
I have a question. I was thinking because it's a primary alcohol, then it would just go all the way to the keto. I'm not sure if it had any stoichiometry had to do with whether it's a hemiketal or a keto. So what's the determinant, whether it stops at the hemiketal or the keto?
So usually when you have 2 equivalents of an alcohol, it will form a ketal, but only because reacting with a ketone is easier than reacting with a hemiketal. So because after you added that alcohol to the ketone, it forms hemiketal, and the extra alcohol added to the ketone will cause more steric hindrance. So it would be easier for an alcohol molecule to be added onto a ketone instead of a hemiketal. So usually it would all it's more likely to finish forming the reaction will finish forming the hemiketal before it will add another alcohol. So that's why you need a second equivalent of an alcohol.
So the answer was what? The ketal or the hemiketal?
So the answer is this. Sorry, did I not share? Sorry, yeah, the answer is a hemiketal. So okay. When it's 1-to-1, the ketone will add 1 alcohol, so that would form a hemiketal. But then when you add an extra equivalent, so 2 equivalents of an alcohol, it would form into a ketal.
Got it. Thank you.
No problem. All right. Any other questions? Sorry, I didn't realize I didn't put the answer up. All right, so I'll move on to the next topic. So next, I'm going to go into Enolate Chemistry and Aldol Condensation. So an enolate, so aldehydes and ketones, they exist in solution as 2 isomers due to the acidity of the alpha hydrogen. So the alpha hydrogen is the oxygen right next to the carbonyl carbon. So that hydrogen is attached to the carbon next to the carbonyl carbon. So as a result, you have keto and enol tautomers. So They ketones and aldehydes, they exist in solution as these two molecules on the bottom. So the double bond will either be between the carbonyl carbon and the oxygen, or between the carbonyl carbon and the alpha carbon. So as a result, we have two tautomers, and the equilibrium between them usually lies more on the keto side. So the left one, the left one on the bottom. So that's the keto tautomer. That's when the double bond is between the oxygen and the oxygen and the carbonyl carbon. This is because it's more favorable to have the double bond rest between the more electronegative oxygen than the alpha carbon. But you can interconvert between the keto and the enol tautomers. So that when you convert between them, it's called enolization or tautomerization. So a lot of the reactions, they involve converting between the keto and the enol form, or enolate. It's called the enolate form when the molecule has a negative charge on it. So on the bottom, these are the two keto and enolates. So the first reaction involving an enolate is called the Michael addition. So this is when the carbanion attacks a multiple bond next to the carbonyl. So this is when you deprotonate the alpha carbon. So because of the acidity of the alpha hydrogen. So when you use a base to deprotonate that alpha carbon, you get a carbanion, and you can resonate the carbanion, the negative charge on the carbanion, onto the oxygen, as you can see in this diagram. And you can use that negative charge to form a covalent bond. So what happens is you resonate down, you resonate the negative charge from the oxygen down, and use that negative charge to attack either a double bond or a triple bond on another molecule. So this molecule on the bottom line, you see the molecule with the dotted lines that is used to represent the negative charge resonating between the two carbonyls. But you can use that negative charge to attack this double bond on the molecule on the left, and that resonates the double bond, the electrons on the double bond onto that carbonyl oxygen. And if you look on the bottom right, it forms this molecule where the alpha carbon on the first molecule is attached to the one of the carbons involved in that double bond in the second molecule, and that carbonyl on the second molecule can reform when taking a proton from the solvent. So it forms this molecule on the bottom right, where it's two molecules attached to each other through a covalent bond. And this is called a Michael addition. So general mechanism is you deprotonate the alpha carbon, and the alpha carbon has a negative charge, and you use that negative charge to attack a double or triple bond in order to form a covalent bond. So it looks like you just drew a line between the alpha carbon and one of the carbons in another molecule involved in a double bond. So that's what the general mechanism looks like. That's called a Michael addition. Next, I'm going to go into Aldol condensation. So this is also a nucleophilic addition to a carbonyl. but the ketone or aldehyde acts as both the electrophile via the keto form and the nucleophile via the enolate form. So this forms a carbon-carbon bond as well. Similarly, the enolate ion is formed using a base, so it's deprotonated using a basic solvent. And this causes the enolate to be more nucleophilic than the enol form because it is negatively charged after deprotonation. So what happens is that nucleophilic enolate will react with the electrophilic carbonyl group of another molecule. So when you have just an aldehyde with a basic solvent or just a ketone with a basic solvent, you can do an aldol condensation. And what this forms is called an aldol product because it has both aldehyde and alcohol functional group on the same molecule. So it has both an aldehyde and an alcohol attached to that same molecule. And it's called a condensation reaction because when you use a strong base and high temperatures, you can dehydrate that molecule and lose a water molecule. But like I said, if you have just one ketone or one aldehyde in the solution, you know what that aldol product looks like. But when there is multiple ketones or aldehydes in that solution, you can't control which acts as nucleophile and which acts as electrophile to attack each other. So you may have multiple products. So this is just the general mechanism for an aldol condensation. So on the top left, these two molecules are the same, but one of them will be deprotonated by that basic catalyst in order to form the enolate ion. And then, so what happens is the negative charge on that alpha carbon will resonate onto the electronegative oxygen, and then you can resonate that negative charge down from the oxygen in order to attack that carbonyl carbon on the other aldehyde. So what happens is that that negative enolate will attack the enol form. So the enolate will act as the nucleophile, and the enol form will react as the electrophile. And what happens is you get this bottom left structure where it's connected together. And so when the enolate ion attacks that carbonyl group, it resonates that double bond. It resonates the electrons on that double bond onto the oxygen, so it causes it to have a negative charge. And that negative oxygen will take a proton from the solvent, the water. So this forms the aldol product. But when you have a strong basic catalyst and high temperatures, you can form the condensation reaction. So what happens is this bottom middle structure, hydroxyl group as a water, and it forms a double bond between the alpha carbon and the carbon that was attached to the hydroxyl group. So that's like aldol condensation. So the last part, the dehydration, it will only occur under basic conditions and high temperatures. So that's an aldol condensation. Any questions before I move on?
Yes, David. Does it always start with the acidic hydrogen, the alpha hydrogen being the one attacked? Why not directly the carbonyl carbon?
Well, the carbonyl carbon doesn't have any hydrogens attached to it, so there's nothing for the base to deprotonate, and it's usually the acidic carbon, the alpha carbon, because of the acidic hydrogens attached to it. So you see here when we deprotonate from the acidic, we deprotonate the hydrogens from the alpha carbon. you can resonate the electrons from that hydrogen that was deprotonated onto the carbonyl oxygen.
So
This
is that always for all carbonyl compounds? Because we saw it earlier also in the Michael addition. So does it always attack the alpha hydrogen first?
So the Michael addition, yeah, it also attacks the alpha carbon. I'm not sure where you saw the carbonyl carbon.
So no, yeah, I don't know. I just made I probably didn't know that
Yeah,
I
so
just assumed.
for
Go
aldehydes
ahead.
and ketones, the alpha hydrogens are acidic. That's because the when it's deprotonated, you can resonate those electrons onto the oxygen attached to the carbonyl, and that's more favorable because oxygens, they're more electronegative and they're better to hold the negative charge.
Okay.
So yeah, it's yeah, for both Michael addition and Aldol Condensation, you wanna work with the alpha carbon, the one with those acidic hydrogens. All right, any other questions? You put in the chat or unmute. All right, I'll move on to the next topic. So next is carboxylic acid derivatives. So I kind of went over a little bit in the last lecture, but I'm going to go over it again. So carboxylic acids, these are carboxylic acid derivatives. They're formed by condensation reactions with carboxylic acids. So normally they're formed from they're formed starting from carboxylic acids. So what happens is the hydroxyl group of the carboxylic acid and the hydrogen from that nucleophile added are lost as a water, so H2O. And then what happens is that nucleophile replaces that hydroxyl group on the carboxylic acid, and it forms a new functional group. So as you can see on the bottom, they all include a carbonyl group. That's their defining feature. But then instead of the alcohol group that is attached to the carbonyl carbon, as in carboxylic acids, they have different groups attached to them. So the anhydride, it looks similar to a carboxylic acid because it's actually two carboxylic acids reacting with each other in order to form this anhydride. So it's like two carboxylic acids combined into one. Ester, so it's a carboxylic acid reacted with an alcohol group, so an OR group, in order to form that ester. So the OR group will replace the OH hydroxy group in a carboxylic acid. And then amide, so either ammonia or an amine group will replace that hydroxyl group in a carboxylic acid in order to form an amide. So I'm going to go further in detail about the carboxylic acid derivatives. So amides, they usually have the general structure, general formula RCONR2. As you can see on the bottom right, that's the general structure of a amide. So it has the carbonyl carbon double bonded to that carbonyl oxygen, and an OR group, an R group attached to the carbon, but then instead of an OH group attached to it, it has a nitrogen attached to it, and it can have two alkyl groups attached to it. So these R's, they can be alkyl groups or they can be just hydrogens. So it can have one carbon chain attached to it, two carbon chains attached to it, or no carbon chains, depending on what the starting amine was. So like I said, it's a carboxylic acid or any of the other derivatives reacted with a ammonia group, NH3, or an amine group. It has to be a secondary or a primary amine group. So it can only have one or two one or two carbon chains attached to it. If the amine group has 3 carbon chains to attach to it, then you can't use that to form a amide group. And because the amide might have hydrogens attached to that nitrogen, it might be able to hydrogen bond. So if the starting group was an ammonia or a primary amine, then it will either have 1 or 2 hydrogens attached to that nitrogen, so it can hydrogen bond. But if it's a secondary amine, then the nitrogen won't have any hydrogens attached to it, so it won't be able to hydrogen bond. And you can have a cyclic amine, and those are called lactams. So when a molecule has an amine group and also a carboxylic acid attached to the same molecule, then you can form a cyclic amine where there's an intermolecular bonding to form a cyclic amine, amine, I mean, and those are called lactams. So next, esters. Like I said, it's formed by reacting with carboxylic acid or one of the derivatives in order in a reaction with alcohol. And this is also a dehydration reaction because it loses a water molecule as a side product. And it's called a synthesis reaction because you combine 2 molecules into one. And the most common ester synthesis is called Fischer esterification. So this is when an ester is formed under acidic conditions from a carboxylic acid and an alcohol group. So as you can see on the bottom, when you react an carboxylic acid and an alcohol group under acidic conditions, you form an ester product, and also the molecule loses water as a side product. So that's ester. Esters, they lack hydrogen bonding because as you can see, the ester group, it doesn't have any hydrogens attached to either oxygen. So because there's no hydrogens attached to either of the oxygen groups, there is no hydrogen bonding between esters. And you can also have cyclic esters as similar to amides, and cyclic esters are called lactones. The most common form of an ester in our body are called triacylglycerols. So this is the storage form of fats in our body. This is when esters of long-chain carboxylic fatty acids. This is esters formed from long-chain carboxylic fatty acids and glycerol. So glycerol is the alcohol group, and then the fatty acids are the carboxylic acids. And when the 2 react with each other, they form triacylglycerols, which is a form of an ester. And a reaction called saponification. This is when fats are hydrolyzed under basic conditions to produce soap. So esters can be hydrolyzed under basic conditions in order to produce soap. And you can add acid to the soap in order to regenerate the fatty acids. So that's esters. Next are anhydrides, also commonly referred to as acid anhydrides. They are formed through condensation reactions of carboxylic acids. So when you react the same carboxylic acid with each other, you form a symmetrical molecule where if you cut the molecule down the middle of the oxygen between the 2 carbonyls, you get identical molecules. But when you react 2 different carboxylic acids with each other, then the molecule won't be symmetrical. So you can see on the bottom, 2 carboxylic acids if they have the same R group, then you will form a symmetrical anhydride, but when the two R groups are different, it won't be symmetrical. And it's also a dehydration synthesis because you lose water as a side product, and you combine two molecules into one. Any questions before I go on to this problem? Okay, all right, I'll give everyone this problem. So which class of compounds has the general formula RCOOR? So you can, usually I try to draw out the molecule, so find out where all the groups connect. So take a few minutes for this question. Let me start the poll. All right, give this question a shot. All right, I'm gonna stop the poll in a few seconds if you want to get your answer in. Okay, I'm gonna stop the poll now. All right, most people will pick choice C, and yeah, that's the correct answer. So as you can see, you can kind of draw out the structure of this. So you have an R group, and that's connected to the carbon, and there's two oxygens connected to this carbon, right? So you know one of them has to be a double bond in order to have those 4 bonds connected to the carbon, and then the R group has to be attached to the single bonded oxygen. So this is the general structure of a ester group. Any questions on that? I'll move on to the next topic. So just some reactions involving carboxylic acid derivatives. So first, I'm going to go over anhydride cleavage. So this is when you react a anhydride with a molecule, and that causes the anhydride to split into two. So it's a nucleophilic acyl substitution reaction that splits the anhydride into two molecules. So, like I said before, you can interconvert the acid, carboxylic acid and its derivatives. So you can change an anhydride into an amide. When you react an anhydride with ammonia or an amine, so what happens is the anhydride reacts as an electrophile, and the ammonia or the amine as the nucleophile, and this splits the anhydride into two. So you form one amide and one carboxylic acid from an anhydride group when that happens. So this is similar to, it's like the opposite reaction of forming an anhydride. So instead of reacting two groups to form anhydride, you react a group with an anhydride in order to form two other functional groups. Similarly, ester formation, when you react an anhydride with an alcohol group, the anhydride reacts to the electrophile, and the nucleophile is the alcohol. This forms an ester group and a carboxylic acid. So the side of the anhydride that reacts with the alcohol turns into an ester, and then the other side forms a carboxylic acid. And same thing, you can reform that carboxylic acid that formed the anhydride when you react the anhydride with a water molecule. So you reform the two anhydrides that were used in order to create that anhydride. So this is the general mechanism for anhydride cleavage. So in this reaction, you react an anhydride with an alcohol group. So when that alcohol group attacks that carbonyl carbon, it forces the electrons from the double bond onto that carbonyl oxygen, and the oxygen in the middle between the two carbonyls, it takes a proton from that alcohol group, and as a result, you have the negative oxygen from the carbonyl and the positive oxygen from the middle of the molecule. In order to break it off, what happens is the negative charged oxygen will resonate the electron down to reform that double bond, and it breaks off the other molecule when the electrons from the carbonyl carbon and the oxygen go on to the oxygen in the middle of the group. So what happens is the alcohol, the carbonyl that was attacked by the alcohol group will form an ester, and then the other side forms this carboxylic acid. So this is anhydride cleavage. When you do cut an anhydride and reform the carboxylic acid, and then whatever the nucleophile was will determine what the other side of the anhydride forms when it's cleaved. Next, I'm going to go into transesterification. So this is when you change the type of ester the molecule is. So this is when an alcohol acts as a nucleophile and displaces the esterifying group on the ester. So this is when a new alcohol attacks that ester in order to kick off the alcohol originally on that ester in order to form a new ester. So the ester transform into a different ester. As you can see, it's a similar mechanism. So the alcohol, the red alcohol, so this new alcohol group will attack the carbonyl carbon, resonate the electrons from lone pair onto the oxygen, and this forms this tetrahedral intermediate in the middle, and you can reform the carbonyl because alcohols are good leaving groups. So what happens is the electrons from that negatively charged oxygen will resonate down to reform that double bond. And as a result, it kicks off this red OR group. It kicks off this blue OR group. So the original alcohol group attached to the ester. And when it kicks it off, it forms this new ester with the red OR group instead. So this is when transesterification is when you convert an ester into a different ester by using a different alcohol group. So this is transesterification. And next I'm gonna go into amide hydrolysis. So this is when you cut an amide group into the original carboxylic acid and ammonia or amine group. So the amide, it can be hydrolyzed under acidic or basic conditions, and this is done via nucleophilic substitution. So what happens is the carbonyl oxygen will accept. So in acidic conditions, the carbonyl oxygen will accept a proton from the solvent. This causes the molecule to have a positive charge, and this allows alcohol to attack via a nucleophilic substitution. So when the water group attacks the molecule, it forms the tetrahedral intermediate that you see on the top right. And what happens is the amide the amine or the ammonia group that was attached to the carbonyl carbon, it will accept a proton from that water group that was added. As a result, it protonates the amine or ammonia group and makes it a good leaving group. So one of the OH groups can resonate down to form a double bond in order to kick off that ammonia or amine group. So this reforms the carbonyl and it kicks off the amine or an ammonia group. So this is the opposite of amide formation. So amide hydrolysis, you reform the original carboxylic acid and the ammonia or amine group that you used to form that amide in the first place. So this is the reverse of an amide formation. Any questions on the lecture before I go into the problem? I see esterification. Sorry, Samantha asked what's the difference between esterification and transesterification. So esterification is when you originally start with a carboxylic acid and you attack with a alcohol group, and this transforms the carboxylic acid into a ester group. But transesterification, trans as in like change, so you change the ester. You change the ester group by attacking it with a different alcohol. So let's say like the ester has an alcohol group with like three carbons attached to it. So let's say this original alcohol is like 3 carbon groups. This new R may have 4 carbons attached to it. And when you perform the transesterification reaction, you change the alcohol group attached to it, and this changes the ester. So instead of an ester with an R group of 3 carbons, you have an ester with an R group of 4 carbons. Does that make sense? sorry. Any questions, comments, concerns before I can run this last question? All right, so I'll give everyone this question. The following tetrahedral intermediate reforms a carboxylic acid. What will be its leaving group? So let me start the poll. Take a few minutes for this problem. All right, I'm gonna stop the poll in a few seconds if you want to get your answer in. I'm in the poll now. And the answer is choice C. So choice, as you can see in this molecule, the only good leaving group is this molecule this group right here. OHs aren't good leaving groups unless they're protonated, and this alkyl group is not a good leaving group. So the only good leaving group is this OCH3 right here, and choice A is the trick answer because OCH3 would have a negative charge, and usually so when molecules have, when it leaves with a positive negative charge, that's not favorable. So it would have to be usually a neutral leaving group. So when it leaves, this OCH3 will pick up a proton in order to form HOCH3. So that would be choice C. Any questions on this problem? And that's the end of the lecture for today. Thank you everyone for attending. Any questions on anything in this lecture from tonight? Thanks, Mark, for tuning in. Thanks, Mark, for helping out. Everyone for tuning in. All right. If you have any questions, you could put in the chat or just unmute.
So David, during these attacks, nucleophilic and addition attacks, if it doesn't have the acidic alpha hydrogen, it attacks the carbonyl carbon.